Pendulum. Explain why timing 10 oscillations gives a more accurate result for the period t than timing 1 oscillation. Timing errors less significant have a smaller percentage uncertainty. The error is spread over 10 periods is divided by 10. Reaction time, human error, a smaller part of time measured. Explain with the help of a diagram how you would use a meter rule and set square to measure the length d of a pendulum as accurately as possible. Clear diagram showing use of set square and rule with horizontal line of set square across to vertical rule from approximate center of bob. Rule position to enable measurement of d from bottom of clamp 1. Wording to include perpendicular viewing of the rule. How you would measure the size of an oscillation. Rule or protractor used. Method explained. Diagram drawn. Investigate the motion of an oscillating meter rule. How to ensure that the meter rule is horizontal. Measure distance of rule from bench at 2 places. And horizontal if equal. Suggest why it is useful to take a trial reading for this experiment. Any suggestion with reference to checking if t measurable, checking if d value appropriate, establishing a range of d and t values. Determining the weight of a meter rule. Example. How the student makes sure that the rule is horizontal before taking the readings. Ensure distances from bench at both ends are equal. Or use set square between rule and stand or line with known horizontal line, e.g. window ledge. Measure distance from bench at each end and check equal. Placing the 2.0 n weight on the meter rule at the correct value of L is difficult. Suggest a more precise method of applying a 2.0 n load to the meter rule in this experiment. Explain why this method is an improvement. Hang load from cotton loop on meter rule and cotton can be placed on precise mark on meter rule. Suspend load from loop of thread. Suggest one possible source of inaccuracy other than the difficulty described above. Assume that the experiment is carried out carefully. Test load not exactly 1.0 n. Spring extension not linear. Meter rule not uniform. Explain briefly how to place the object as accurately as possible with its center at the 10.0 cm mark. Equal readings either side of the 10 cm mark. OR. Average of readings either side of the mark equals 10. Investigating spring. Precautions that the student should take when measuring the length of the spring to ensure an accurate reading. Any 2 valid precautions, e.g. Rule close. Rule parallel to spring. Eye perpendicular to reading. Use set square. Clamp rule. A student improves the experiment by taking additional sets of readings. Suggest the additional apparatus that the student uses. Suggest how the student uses the additional results. Additional loads. Plot a graph or take an average. Determining density. Explain briefly how to use the string and the meter rule to determine the circumference C as accurately as possible. Wind string round beaker several times. Measure the length of the string and divide by the number of turns. The student uses a measuring cylinder to measure the volume of dry sand. Draw a diagram of the measuring cylinder and show the line of sight that the student must use to obtain an accurate volume reading. Diagram showing a clear line of sight drawn at right angles to measuring cylinder level with the top of its contents. Another student wants to obtain a more accurate value for V1. He uses the method of floating the block of wood in water. Suggest how the student could obtain a more accurate value by taking a measurement. Float wood and mark water level, remove and mark the water level. Measure submerged depth and multiply by the cross-sectional area. OR. Measure height of block that is not submerged 1. Multiply by the cross-sectional area. OR. Measure height of block that is not submerged 1. Multiply by the cross-sectional area, then subtract from total volume of block. 1. OR. Use of a measuring cylinder, displacement can 1. Measure the volume of water displaced by the floating block. Finding the density by immersing an object in a beaker of water. Suggest a possible source of inaccuracy in the determination of P in this experiment. Part of load U is metal. Hanger immersed 2. Clay wet when weight measured. Air holes in clay. Air bubbles on immersed clay. Investigating the cooling of hot water in 2 different cups. Describe one precaution that you would take to ensure that temperature readings in the experiment are as accurate as possible. Line of sight perpendicular to scale. Wait until reading stops rising at start. Stir before reading. State 2 precautions taken when reading the volume of water in a measuring cylinder in order to obtain an accurate result. View scale value water level at right angles perpendicularly to bottom of meniscus. The student records the volume 5 to the nearest 1 cc. Suggest why this is appropriate. The measuring cylinder can only be read to nearest 1 or 2 cc. OR to nearest cm3 means you are measuring the volume to 3 significant figures, which is sufficient. Which one is more effective in reducing the cooling rate of hot water? Clear statement that cup B is more effective. Comparison of temperature changes over 180°, matching statement. Suggest an additional experiment to show how the lid affects the cooling rate of cup A. Explain how to use the additional results to show the effect. Repeat cup A experiment without a lid. Calculate cooling rate and subtract XA. Comparing the effect of the materials of the cups on cooling rates. Suggest 2 variables that she should control to make this test fair. Same volume of water, same initial temperature, same diameter, height of cup, same room temp, named appropriate environmental condition. Suggest a change to the apparatus or the procedure to produce a greater difference between rate of cooling of A and B. Thicker, more insulated lid. Higher initial temperature. Explain why the mixture of hot and cold water should be stirred before taking the temperature reading at the start of the experiment. To obtain even temperature throughout. A student suggests that glass is a thermal insulator and the experiment does not just test the effect of the air gap. Suggest one change to the apparatus that would test the air gap more effectively. Use conducting material, metal for beaker B. Support beaker A in beaker B so that there is an air gap underneath too. Possible constant variables. Initial temperature, volume of water, room temperature or other appropriate environmental condition. Conduction through sides, insulation. Evaporation from the water surface, lid. Investigating thermal properties of X and Y. Explain what the student does after pouring the hot water into the sand and before taking the temperature in order to obtain a reliable value for theta m. Stir it. Miscellaneous. State how the graph line shows that the load and extension are directly proportional. Straight line. Stated as going through origin. RMB to draw a triangle for the gradient. Ask whether or not the results support this suggestion. Justification. Obtain values plus values very close, within limits of experimental accuracy. Since the ruler can go up to 1D, page, must put 0.0 if necessary. Describe how the experiment could be improved to make the readings more reliable. Repeat each reading and calculate average value. Why something should be read at right angles. To prevent parallax errors. If the statement does not match the results too different so as beyond the limits of experimental accuracy. Values not close enough too far apart greater than 10% difference. Explain briefly how a graphical method, e.g. by plotting a graph of UV against D, can give a more accurate value for the focal length. A straight line is a way of taking an average. Anomalous results can be seen and repeated or ignored. Explain how the student can decide whether the values of resistance are the same within the limit of experimental accuracy. Check to see if the results are equal, close, within 10%. Electricity. A student determines the electromotive force E, M, F, and resistance of a cell by using a resistance wire. Suggest how the experiment and the graph could be improved to obtain a more accurate value of E, M, F. E. Obtain more values at other potential differences. Start V-axis at 3.0 V to expand scale. Investigate resistance. She connects the second resistor in parallel with the first resistor. She connects the voltmeter across both resistors. She records the potential difference V3 across the resistors and the current I3 in the circuit. Draw the circuit. Investigate resistance. Investigate the RS between the combined resistance of identical resistors connected in parallel and the number of resistors. Use another resistor. Add at least 3 more resistors, one at a time. A student wishes to determine the resistance of lamp RL when the potential difference across the lamp V1 equals 0.0 V. Describe how the experiment can be extended to do this with the help of a suitable graph. Obtain more values and plot a graph of RL versus VL. Extend line to RL axis and red intercept. Investigate an electrical circuit. Explain one advantage of using a variable resistor to vary the current compared to the procedure carried out. Can obtain continuous set of values. More straightforward to change current. Can obtain more values easily. Investigate the resistance of samples of wire. Explain how you would change this experiment to investigate the relationship between the length of a sample of wire and its resistance. Use different lengths of the wire sample. Measure the P, D, and current. Determine the resistance of each length. Explain how the use of a potential divider may give a more reliable value for R1. Can obtain average value. Plot a graph. Values of resistance that can be used. At least 4 additional values suggested. 1. All values within omega to 20 omega. Investigate the resistances of 2 wires. Suggest one reason why students all doing this experiment carefully with the same apparatus may not obtain the same results. Crocodile clip connection not even. Difficult to connect at exactly the correct length. Resistance wires not uniform. Investigate resistances of combinations of resistors. A student thinks that the 3 resistors Ra, Rb and Rc have the same resistance within the limits of experimental accuracy. Suggest how the student could use the apparatus provided to test his idea. Use of a voltmeter and/or an ammeter. 1. Measure V and I for each resistor and calculate ROR. Connect each resistor to the same voltage supply and measure the current OR. Connect resistors in series and measure the voltage across each of them. OR. Connect resistors in parallel and measure the current through them. Investigate the refraction of light by a transparent block. A student places 2 pins, P1 and P2 on line N. Suggest whether the 2 pins are a suitable distance apart for accurate ray tracing. Not suitable, should be as far apart as possible. Precaution to ensure accuracy. Look at base of pins. Keep pins vertical. Use thin pins. Thin lines. Pins. Sharp pencil. Use large pin separation. Securely attach the ray trace sheet to the surface. Suggest why different students, all carrying out experiment carefully, may not obtain identical results. Difficult to align pins. Place pins accurately. Pins too thick. Lines too thick. Pins for separation must be at least 5 centimeters. Normal in center of AB to 2 millimeters and at 90 degrees. A student plans to test the suggestion that, in this experiment, I equals theta for all possible values of I. Explain briefly how you would test the suggestion. Repeat experiment using more I values. 1. Uses at least 4 I values. A student plans to test the suggestion that, in this experiment, BA is a constant for all possible values of I. List suitable values of I that the student could use. At least 4 additional values, all less than 90. Range at least 30. Investigate the image produced by a converging lens. A student decides to extend the experiment using larger values of U. Explain why this could produce less reliable values for W. Distance between the lens and the illuminated object gets bigger and bigger, so the image produced gets smaller. Suggest an improvement. OR. Explain why method 2, using illuminated triangles and bringing the lens closer to the screen, is less accurate. As long as the image is very small. Any suitable explanation, e.g. values of high become very small. Difficult to measure. OR. Difficult to measure the height of the image as the image is small. Greater % uncertainty. Any suitable improvement, e.g. use a larger object. Use graph paper on screen. Mark top and bottom of image and measure after. Suggest one practical difficulty with this experiment. Explain briefly how you would try to overcome this difficulty in order to obtain accurate results. Deciding the screen position for most clearly focused image. 1. Move screen slowly backwards and forwards. 1. OR. The image is difficult to see. 1. Carry out in a darkened room, away from bright lights. 1. OR. Meter rule moving. 1. Clamp rule, tape rule to bench. 1. OR. The image is small and difficult to focus. 1. Use a bigger object. 1. OR. Difficult to find the center of the lens. 1. Use a marked lens holder. 1. OR. Object, center of lens and screen are not at the same height above the bench. 1. Use a ruler, set square to check. Describe one difficulty that can be experienced when measuring the height of the image. Suggest an improvement to overcome this difficulty. Any difficulty in measuring height, e.g. ruler in way of light. Difficult to see top and bottom of image. Edges of image blurred. Difficult not to move screen when placing ruler to measure image. Matching solution, e.g. use graph paper on screen. Mark top and bottom of image and measure later. Use translucent screen and measure it back. Use larger object, clamp screen, after obtaining focus. Investigate the focal length of a converging lens. If the question says, move screen, then OK. Briefly describe a technique to obtain an image on the screen that is as sharp as possible. Move screen backwards and forwards slowly. State one precaution to ensure that the measurements of U and V in this experiment are as reliable as possible. Focus on distances. Mark position of lens on holder. Clamp rule, place rule on bench. Ensure screen, lens and object all perpendicular. View scale perpendicularly. When the question says, moves the lens. Precautions. Use darkened room, bright object. Move lens slowly to find sharpest image. Move lens back and forth to find sharpest image. Ensure that object, lens and screen are vertical. Object and center of lens same height above bench. Perpendicular reading, viewing of the ruler scale. Mark the center of the lens on its holder. Investigate the magnification of the image produced by a lens. Focus on precautions to ensure accurate readings. Image's clarity, moves the screen until a clearly focused image is formed on the screen. Use dark room, bright object, move screen slowly to find best image. Mark center of lens position on lens holder. Place meter rule on bench, clamp rule in position. Ensure object, lens and screen are vertical. Ensure object and lens at same height from bench.